For damped, harmonically forced structural systems, the effect of varying the frequency of the forcing function relative to the natural frequency of the structure can be analysed using the dynamic magnification factor. Before we proceed, it is instructive to develop some basic mathematics. The harmonic addition theorem states that it is always possible to write the sum of a sinusoidal function, so in this case f theta equal to a times cosine theta plus b times by sine theta as a single sinusoid of the form f theta equal to c cosine theta plus delta. Using this theorem, we will then show that the particular integral up of t equal to g1 cosine omega t plus g2 sine omega t can be written as upt equal to u0 sine capital omega t minus phi. Using the following trigonometric identity, we see that sine alpha plus or minus beta is equal to sine alpha cosine beta plus or minus sine beta cosine alpha. Comparing this equation 5 to equation 4, we can firstly say that looking at the right hand side of equation 4, u0 sine capital omega t minus phi is equal to u0 sine capital omega t cosine phi minus u0 sine of phi cosine omega t. Since these are both equal to the particular integral, then the right hand side of equation 6 is also equal to the right hand side of equation 3. So we can say then that u0 sine capital omega t cosine phi minus u0 sine of phi cosine capital omega t is equal then to g1 cosine omega t plus g2 sine capital omega t. Now it should be clear that by inspection that g1 is equal to minus u0 sine of phi and g2 is equal to u0 cosine of phi. We can see this by comparing the two expressions. So we see here that we have g1, and this is multiplied by cosine capital omega t. On this side of the equation, we've got cosine capital omega t multiplied by minus u0 sine of phi. So we can then say that g1 is equivalent to minus u0 sine of capital phi. Similarly, we have g2 multiplied by sine of capital omega t, and this can be compared to u naught to sine capital omega t in this equation here. So we can then say that G2 is equivalent to u naught times by cosine theta here. So we'll label these equation 8. From this we can also say that tan of phi is equal to sine of phi over cosine of phi, and that is then equal to minus G1 over G2, because these two cancel out in equation 8. So if you divide these through, it then becomes obvious that u naught and u naught here cancel out, so the ratio of sine theta over cosine theta is equal to minus G1 over G2. Then inverting this to get the angle phi, we have the inverse of tan times by G1 over G2. Also, if you take the sum of the squares of G1 and G2, you end up with u naught squared times by sine squared of phi plus cosine squared of phi. We know then that this is always equal to 1. So u naught then is equal to the square root of G1 squared plus G2 squared. Remembering from before that G1 is equal to P naught over K times by minus 2 zeta beta divided by 1 minus beta squared all squared plus 2 zeta beta squared, and G2 is equal to P naught over K times by 1 minus beta squared over 1 minus beta squared all squared plus 2 zeta beta all squared. So adding these two up, we have G1 squared plus G2 squared is equal to P naught over K squared times by 2 zeta beta squared plus 1 minus beta squared squared divided by 1 minus beta squared all squared plus 2 zeta beta squared, and then this whole thing is also squared. Simplifying this out, we then end up with P naught over K all squared times by 1 over 1 minus beta squared all squared plus 2 zeta beta all squared. Since u naught, as we said before, is equal to the square root of G1 squared plus G2 squared, we can then say that u naught is equal to P naught over K times by 1 over the square root of 1 minus beta squared all squared plus 2 zeta beta all squared. Going back to equation 4, we said that UPT is equal to U0 sine capital omega t minus phi. Substituting in for U0, we now have P0 over K times by 1 over 1 minus beta squared all squared plus 2 zeta beta all squared times by sine capital omega t minus phi. We can then write this as U static times by this new value Rd times by sine capital omega t minus phi, where Rd is equal to U0 over U static, and that's equal to what we derived as being 1 minus beta squared all squared plus 2 zeta beta all squared. And this is what we call the dynamic magnification factor. Finally, we said that phi was equal to tan minus 1 times by 2 zeta beta over 1 minus beta squared. This is what we call the phase angle, and this defines the time by which the response lags behind the applied force. Sketching out roughly the dynamic magnification factor, we'll have beta, which is the ratio of the forcing frequency to the natural frequency on the x-axis, and Rd on the y-axis, and we will then see that as this tends to 1, we get the peak response. A more detailed and accurate graph of this is shown in your lecture notes.